Assalamu alaikum. Today we shall talk about the formation of energy band in solid. We said that in semiconductor there is a small energy gap between the valence band and the conduction band, and the gap is such that at room temperature there will be a significant number of electrons transferred from the valence band to the conduction band, so that when a potential is applied, it conducts current. The conductivity will be less than the conductivity of a conductor, but it will not also be zero. Today we shall discuss how these energy bands are formed. So we start with the energy band or energy level of hydrogen atom, then gradually we will move to discuss the formation of energy band of silicon. So here we show the energy levels of hydrogen atom. Here n is the principal quantum number. So n equals 1 is the ground state, and the electron in the hydrogen atom stays in this state, and the energy of the ground state is minus 13.6 electron volt. Now if we go to the higher states like n equals 2, 3, 4, we see that the energy increases. Now when n goes to infinity, that is n becomes very high, the energy of the electron becomes 0 and the electron become free. So this value minus 13.6 electron volt means when the proton and the electron came together to form the hydrogen atom, this amount of energy is released. So to break the bond between the proton and the electron in a hydrogen atom, we have to supply 13.6 electron volt energy. Now there is a very important thing here. See, this is the ground state n equals 1 and n equals 2 is here. Electron cannot sit in between these two states. Electron can either sit n equals 1 or at n equals 2 level or at n equals 3 or like that. Electron cannot sit between two adjoint energy levels. That means the energies of the electron is discrete, that the values of the energy levels are discrete. So there are the allowed energy states where electron can sit, and these are the forbidden area where electron cannot sit. Now let's look at the formation of hydrogen molecule. So we have two hydrogen atom. Here I have shown that they have the up spin, one have up spin and another have down spin, but they both can have up because they are not related. So the two hydrogen atom, they are far from each other. There is no interaction between them. The electron in these atoms can have any spin. So when we bring them together to form the hydrogen molecule, the energy levels split. They form a bonding state and an anti-bonding state. Since the electrons tend to occupy the lowest energy level, both of the electrons tends to go to the bonding state, and in this case they have to, one have to be up, another have to be down spin. Since this energy is lower than the anti-bonding state, and electron tend to go to the lower energy state, we have hydrogen molecule. Now this is how the hydrogen molecule is formed. Now let's look at the helium atom. In helium atom, in 1s there are 2 electrons, and then when 2 helium atom come together, they form bonding and anti-bonding state. Since both helium comes with 2 electrons, then when 2 helium atom come together, we have 4 electrons. Therefore, both the states, bonding and anti-bonding states, are occupied. That means they tend to stay separate, because to occupy this, this is higher energy than this one. So the helium atom prefer to stay as atom. They don't form molecule. Now there is one important thing from these two. We learn that atomic energy levels split when we bring the atoms together and they form the molecular energy level. So this is the molecular energy level and this is atomic energy level. Since in hydrogen, molecular energy level has lower energy than the hydrogen atom's energy, they tend to form the molecule. But in helium, the anti-bonding state has higher energy than the atom. Therefore, they don't tend to follow, they don't tend to form molecule. The helium stays as atom. Now, let's look at the lithium. So, lithium has 3 electrons, 2 goes to 1s and another one goes to 2s. When the lithium atoms are far from each other, there is no interaction. The energy levels are like this. So here I didn't show any value, just take an arbitrary value. When we bring the lithium atoms together, say we have n number of lithium atoms together, now we will have n electrons in 2s, so there will be n orbitals. Now, in each orbital, there can have 2 electrons. So, they will start to occupy from the lowest level. Then at the half, they will be filled and the half will be empty. So, here I just have shown few lines, but when you have a huge number of lithium atoms, say 10 to the power 23 or something like that, you will have huge number of lines. In that case, in the practical purpose, this will be called band. And if you distribute the electrons, you will see that half of the band will be full and half of the band will be empty. Now, this is how lithium solid is formed. Now, let's look at the silicon. Now, silicon has 3s. All the ground states or the lower states are filled, so we are not showing them. So 3s has 2 electrons, 3p has 2 electrons also. Now when you bring them together, these 2 levels because of hybridization, they form the 4 levels. Now all of them has 1 electron each. So this is the shape after hybridization. Now when you bring 4 when you bring lots of silicon atoms together, and we know that in silicon, 1 silicon atom is bonded with 4 other silicon atoms. So you will have bonding state and you will also have anti-bonding state, and the bonding state will be occupied and the anti-bonding state will be empty. So this will be the valence band and the empty band will be the conduction band. Remember, this is for the one silicon forming bond with the one nearest neighbor. But in the silicon crystal, you have 1 silicon surrounded by 4 other silicon. So all the bands or the states in the valence band will be filled, and there will be a gap, energy gap, and the conduction band will be empty. Now we know that for silicon this gap is about 1.14 electron volt. So this is how the energy bands in silicon is formed. Now here you can see the is silicon having surrounded by 4 silicon, and the is silicon sharing 1 electron with its nearest neighbor, so that this silicon has 8 electrons surrounded by it. Now this is of course at 0 Kelvin. Now what happens at the room temperature? Now at the room temperature, the electrons, some electrons in the field band will have enough energy to jump to the conduction band. This is how this is formed. So it takes energy. It can be thermal energy. It can be light, that is photon. So electron jump from conduction valence band to conduction band. They can conduct, or they can carry current, or they can contribute in the current. So what happens? This was supposed to be here. This electron supposed to be here. Because of thermal energy, it moves, and it leaves a void or empty space. We call it hole. I have shown in here. And at room temperature, there will be 15 billion free electrons in an intrinsic semiconductor of size 1 centimeter cube. So this is huge. Now here I have shown only few, but actually since this number is huge compared to what we can show here, so we actually show like this. So the top of the valence band is empty, that is, this become partially empty, and the conduction band become partially filled. So now when you apply potential, these electrons contribute to the current. This can be understood by an analogy with a glass. Say you have a glass half filled, glass tube half filled. When you tilt it, the liquid flows. But if you have a full glass tube which is full of liquid, and whatever you do, the fluid don't flow. So this is for the conductor, this is for the insulator. But for the semiconductor, it was at 0 Kelvin, it is like this. So even you tilt it, nothing flows. But at the room temperature, this became little bit empty, and the liquid fluid transferred to here. So when you tilt it, both contribute to the flow. Both the fluids move. So both the bands contribute in the conductivity. So we define the semiconductor that it is an insulator at 0 Kelvin, but its band gap is such that at the room temperature, because of thermal excitation or photoexcitation, there will be observable number of electron or carrier in the conduction band. And of course, the temperature needs to be less than the melting point of the semiconductor. Because if it melts, then it becomes liquid, then everything changes. So now the conductivity, we have seen for the silicon, this was the structure at 0 Kelvin. At room temperature, some electrons move and they are free. That means they can move within the silicon system. They are free. That doesn't mean that they can go to everywhere. They are free in the sense they can move within the boundary of the material when you apply a potential. But the conductivity can be increased. Like silicon is in the group 4. So, but if we dope or replace silicon with the group 3 element or group 5 element, then there will be change in conductivity. Say if we replace or dope with the group 5 element, then this is antimony. This is the group 5 element. So it has 5 electrons. So it will have 5 electrons. Now we will have an extra electron to move. So the number of carriers, negative carriers, will increase because of the doping with the group 5 element. That's why this is called N-type semiconductor or N-type material. Now, if we dope with the group 3 element, then there will be an empty space. That is, if it were silicon, it is supposed to have an electron here. But now this is boron, it has only 3 electrons in the outer shell. There will be a void. We call it hole. This is positive charge. So if an electron come from here to this place, this boron will accept it. It will become negatively charged, and this is called acceptor. But if this electron move, then this antimony will become positively charged. This will be a positive ion, and we call this a donor. So how these actually holes flow? Actually, these holes don't flow or don't move. But because of the motion of electron, it look like that the hole is moving. So if the electron come here like this, you will see that the hole moved here. So we say that hole flows. That means the hole flows in the opposite direction of the electron, but it is actually the flow of electron. But for the simplicity, we say that holes flow. Now, in the n-type material, we have electron, that is the majority carriers, because if you remember, we doped with the group 5 element, we have extra electrons. This is the majority carrier. And because of thermal excitation, there will be some electron moving from valence band to conduction band. There will be some hole, but the number will be less than the electron. So the holes will be the minority carrier. So in n-type, we have majority carrier is electron and the minority carrier is hole. And we also have donor ions. The opposite is in p-type material. In p-type, the majority carrier is hole, void. But there will be also some free electrons because of thermal excitation. And these are the electrons. These are minority carriers. At the same time, we will have acceptor ions. Now, we have said that this is for silicon, there is a small gap between the valence band and the conduction band. But when we dope, when the material become extrinsic, not intrinsic, the energy level tend to change. We will talk about this. Just before that, let's talk something more about the band of the semiconductor. Now, in the y-axis, the values are energy. What is the value in the x-axis? Of course, this is position. But this is a simplified structure in the position, the band structure in position. But in the practical purposes, when we plot the bands, we plot them in reciprocal space, and they look like this. This is complicated. So this is a simplified, and this is also in real space, but this is in the reciprocal space. Now, we will not talk about these details, but just to give you hints that the band structure that you see in the literature, they are like this because they are not the simplified version in the real space. They are the real band structure, but they are in the reciprocal space in the K space. We will not talk about these details. So let's go back to this band. So we said that when we dope the semiconductor, say with a group 3 element or group 5 element, whatever, then we have donor and acceptor. If we dope with group 5 element, we have donor ions. If we dope with group 3 elements, we have acceptor. Now the band structure or the bands change, and then in that case, we have a donor band depending on the ionization energy of the donor, and this usually less than the conduction band. And we have an acceptor band. This is higher than the valence band. So if we Okay, let's try to understand this, how this happened and what is the meaning of this. So let's consider this is a two-dimensional structure of silicon. So silicon solids are three-dimensional, but here I have simplified and make a 2D projection of this. So this is a silicon atom. It has 8 electrons. So each line is actually showing, representing an electron. Now, if we dope an arsenic group 5 element, so we'll have an extra electron. So this means that this will be the donor, and the electrons from the donor ion goes to the conduction band and the arsenic become positive. This is what's shown here. Electron is free. It can move within the system. So the donor band will be less than this, and this will be the donor ionization. The gap between EC and ED will be the donor ionization energy. Now, actually, how much dope we do actually? So we usually dope 1 parts per million. That is, in every 10 to the power 6 silicon atom, there will be 1 foreign atom like arsenic here. So doping rate will be 1 ppm, that is parts per million. Now, if we dope with boron, then we will have a hole, the void space, and this become an acceptor ion. So we will have the acceptor energy level here. So it will accept electrons, leaving holes in the valence band. Also, same here, doping is same, 10 to the power 6. In every 10 to the power 6 silicon atom, there will be 1 boron atom. Now you can see there is a small gap between the top of the valence band to the acceptor energy level. This is here about 0.05 electron volt. I have shown some of the values here. So if you dope with a P, the donor level will be here. It's less than this value electron volt to the conduction band. And therefore, if you dope with the boron, it will be about 0.05 electron volt, which is shown here. So these are called weak donors or weak. Sorry, these are weak donors. These are weak acceptors. But this is a strong donor. So the gap change. Use the level of the accepted or level or donor level is very high. So this is called strong donor or acceptors. Now there is one important thing. So that is the effective mass of the electron in the system. Now when we have only the system, the silicon, or the electron, the mass of the electron is, we know, 9.1 into 10 to the power minus 31 kg. But in the system, for these free electrons, the mass is actually not the mass. There is a, because of the acceleration, there is, when you apply force, let me rephrase this. So these are the electrons. This has certain mass. When you apply force or the potential, they tend to move, that is, they accelerate. Now you have force, you have acceleration. So from that we calculate another mass, that is, we call the effective mass. So this is within the system, the acceleration is within the system. Now there is external force, can be from the ion also, it can be from the, because of the applied force. But here when we are talking about the effective mass, this is actually because of the ions. So let me show it again, like this here. So you have positive ions. When electron move, when they come at this close to the arsenic, the positive ion, the ion will tend to attract them because they are of opposite charge. So the acceleration will be different. That's why at different places of the band structure, the effective mass will be different. We will not discuss these, but you can see some of the values. These are the for gallium arsenide, this is for silicon, this is for germanium, and the calculation was done at 300 Kelvin. So you can see this is the effective mass of electron. This is different, so this is not the one. This is normalized with the regular mass of the electron. So the ratio is supposed to be 1, but this is not the case. In silicon, this is 1.08 for gallium arsenide, and for germanium, this is less than 1. This is the effective mass of hole. Now these are these are different, so showing the different at conductivity calculation. These are the density of state calculation. These are different way of calculating. Now here the silicon effective mass of silicon also. These are also the average values for from different places in the band structure. Actually, the effective mass depends on the band structure. So here are some other effective masses. For this is for the electron, this is for the hole, just to show you. Now there's one more thing about the electron and hole. As electron goes to the upper level, the energy of electron increases. Therefore, electron tends to occupy the lower states. But if you go to the opposite direction, the energy of the hole increases. Therefore, the hole tend to occupy the higher energy levels. That's all for today. Thank you.